4.5 billion years ago, there was literally nothing here. No sun, no planets, no Earth. Just a giant cloud of gas and dust floating in the dark. Then gravity kicked in and started pulling everything together. Slowly at first, then faster and faster, and way, way hotter.
And then, boom! The sun fired up for the first time. Nuclear fusion lit off at the core, and all that energy just exploded outward.
But here's the cool part. All that leftover junk around the sun, the rocks, the ice, the dust, they started smashing into each other and sticking together. And over millions of years, that's how the solar system we know today slowly came together. So how exactly did all of that happen? Let's get into it. All right, so everything starts with what scientists call the Solar Nebula. It's basically a massive cloud of gas and dust. We're talking trillions of kilometers wide, just hanging out in space. The cloud was about 74% hydrogen and 24% helium by mass. That last 2%, heavier elements like carbon, oxygen, iron, the stuff that eventually built the rocky planets, including us. Now, something triggered all of this. Scientists think a nearby star went supernova. That explosion sent a shockwave through our nebula and gave it just enough of a push to start collapsing. That push made the cloud start spinning, and as it collapsed inward, conservation of angular momentum made it spin faster and faster, just like a figure skater pulling their arms in. The result was this flat spinning disk called the protoplanetary disk. The center was absolutely scorching hot, the outer edges freezing cold. And that temperature difference turned out to be everything. At the center, gravity kept squeezing all that gas tighter and tighter. The pressure built up so much that the temperature at the core hit around 10 million Kelvin. That's the ignition point for nuclear fusion. At 10 million Kelvin, hydrogen nuclei started fusing into helium, releasing an insane amount of energy. That's nuclear fusion. And just like that, our sun was born. Once the sun was alive and burning, it started blasting out solar wind, a stream of charged particles. This pushed all the lightweight gas and ice way out into the outer solar system. Only the tough stuff could survive that close to the sun, metals and silicate rocks, and they started bumping into each other and sticking. Scientists call these early building blocks planetesimals. This process is called accretion. Small stuff collides, makes bigger stuff. Bigger stuff has more gravity, so it grabs even more stuff. It's basically a cosmic snowball effect that built whole planets. Eventually, these protoplanets got big enough to have seriously massive collisions. We're talking impacts so huge they could melt the entire surface of a planet and reshape it completely. After all that chaos, billions of years of collisions and mergers, we ended up with 4 rocky planets: Mercury, Venus, Earth, and Mars. The inner solar system was finally stable. Mercury is the smallest planet, just 38% of Earth's diameter. It's the closest to the sun and moves incredibly fast. It completes one full orbit in just 88 Earth days. Venus is almost exactly Earth's size, but don't let that fool you. Its runaway greenhouse effect cranks the average surface temperature to about 465 degrees Celsius, hot enough to melt lead. And then there's Earth, the one that got incredibly lucky. It's in the perfect spot, with liquid water, an atmosphere, and a big moon. It's the only planet in our solar system we know has life. Mars is the last of the rocky planets. Evidence shows it once had liquid water flowing across its surface and a much thicker atmosphere. Something went really wrong for Mars, and we'll cover that story in a future video. Here's the thing that really puts it in perspective. Look at the rocky planets compared to the outer ones. It's like comparing a marble to a basketball stadium. The outer planets are in a completely different league. Past Mars, there's an invisible boundary called the frost line, or the ice line. It's the distance from the sun where temperatures drop low enough for water, methane, and ammonia to freeze solid. Beyond that line, there was way more material to work with. Icy planetesimals in huge quantities. That abundance is exactly why the outer planets were able to grow so massive. Jupiter formed first. It built up a massive solid core. Scientists estimate at least 10 Earth masses, maybe much more. Once it hit that critical size, gravity started pulling in enormous amounts of hydrogen and helium gas. The result? Jupiter, the largest planet in the solar system. Its diameter is about 11 times wider than Earth's, and it has more than twice the mass of all the other planets in the solar system combined. Saturn formed the same way as Jupiter, but the leftover icy debris that didn't get pulled in organized itself into those iconic rings. Scientists are still figuring out exactly how that happened. Uranus and Neptune are a different category. They're called ice giants. Not because they're made of regular ice, but because they contain large amounts of water, methane, and ammonia in their interiors. Here's a wild fact about Uranus. It's tilted at almost 98 degrees. It basically rolls around the sun on its side. Most scientists think a massive collision billions of years ago knocked it into that position. Neptune is the farthest true planet from the sun, and it holds the record for the strongest winds in the solar system, up to 2,100 kilometers per hour. That's about 1.7 times faster than the speed of sound. Jupiter's gravity has shaped the entire solar system. It's so powerful that it prevented a planet from ever forming in the asteroid belt. All that material just stayed scattered. And Jupiter also shields Earth from many incoming comets. Scientists also think Jupiter went on a huge road trip early on, migrating inward the sun before Saturn's gravity pulled it back out. This is called the Grand Tack hypothesis, and it explains a lot about why the inner solar system looks the way it does. Okay, and now we gotta talk about the Goldilocks Zone. And yeah, it's named after that fairy tale. Because the concept is exactly that simple. Not too hot, not too cold, just right. The Goldilocks zone, or habitable zone, is the range of distances from a star where temperatures could allow liquid water to exist on a planet's surface. Our Earth sits right in the middle of it. Why does liquid water matter so much? Because life as we know it is completely dependent on it. Water is the best solvent we know. It enables the complex chemical reactions that make biology work. Venus is almost exactly Earth's size, which makes it kind of terrifying. Without liquid water and a stable atmosphere, you end up with crushing pressure, sulfuric acid clouds, and a surface hot enough to melt lead. Earth didn't just get lucky with location. It also has a magnetic field blocking radiation, tectonic plates recycling nutrients and carbon, a large moon stabilizing its tilt, and a liquid iron core driving all of it. It genuinely won the cosmic lottery. And here's the cool thing. Every star has its own Goldilocks zone. The size and temperature of the star determine red dwarf stars, it's very close in. For massive bright stars, it's way farther out. And our galaxy alone has over 200 billion stars. Statistically, some of them have to have planets sitting in the right zone with the right conditions. But finding them? That's a whole other story. Between Mars and Jupiter, you've got the asteroid belt. This is where a planet almost formed, but Jupiter's gravity kept stirring things up and prevented any single body from growing large enough to dominate. The biggest thing in the asteroid belt is Ceres, which is now classified as a dwarf planet. It's about 945 kilometers wide. And here's a wild fact. The total mass of the entire asteroid belt is less than 4% of Earth's moon. Out past Neptune, you've got the Kuiper belt, a disk of icy objects extending about 20 to 50 astronomical units from the sun. This is the main source of some and source of short-period comets. Pluto lives in the Kuiper belt. In 2006, when astronomers realized there were many similarly sized objects out there, like Eris, Makemake, and Haumea, they created the dwarf planet category. The Oort cloud. It surrounds everything, a massive spherical shell of billions of icy objects surrounding our entire solar system, 1 or 2 light years out, halfway to the nearest star. About 4 billion years ago, there was a brutal period called the Late Heavy Bombardment. The inner planets got absolutely hammered by asteroids. The moon still carries those scars, that's why it's covered in craters. But here's the plot twist. Those same asteroids may have delivered water and organic molecules to early Earth. The building blocks of life might have arrived via asteroid, so it was both catastrophe and cosmic delivery service. Let's talk about moons, because they play a huge role in how planets work. Earth has 1, Mars has 95, Saturn has 146. The solar system for 290 confirmed moons total. Our moon formed from one of the most violent events in Earth's history. A Mars-sized body called Theia slammed into early Earth about 4.5 billion years ago. The debris that got thrown into orbit eventually came together as the moon. Our moon isn't just decoration, it stabilizes Earth's axial tilt. Without it, Earth's axis could wobble between almost vertical and nearly horizontal over millions of years, causing climate swings that would make life nearly impossible. Europa is one of the most exciting places in the entire solar system. Under its icy surface, there's a saltwater ocean, kept liquid by water than all of Earth's massive gravity. Titan is Saturn's largest moon and one of the most fascinating objects in the solar system. It has a thick nitrogen atmosphere and actual lakes and rivers, but they're liquid methane, not water. It's the only moon besides Earth that has stable surface liquids. Are we alone? The Drake equation estimates how many communicating civilizations might exist in the Milky Way. It multiplies factors like star formation, planets, and life probability. The math gets wild. But then there's the Fermi paradox. If the universe is this big and this old, where is everybody? We've been scanning the skies for decades and haven't picked up a single confirmed signal from another civilization. That silence is deeply unsettling. We've now confirmed over 5,700 exoplanets, planets orbiting other stars. Many of them are in their star's habitable zone. The solar system's formation story isn't unique. It plays out all across the galaxy. Here's what's eventually coming for our solar system. In about 5 billion years, the sun runs out a hydrogen giant and swallowing Mercury and Venus. Earth's fate is less certain, but it won't be pretty.
After the red giant phase, the sun will shed its outer layers and collapse into a white dwarf, roughly Earth-size but with most of the sun mass packed in. The outer planets will keep quietly orbiting it for billions of years to come.
All right, let's recap. A giant cloud of gas and dust. Gravity collapsed. The planets built this giants formed past the frost line. Earth got incredibly lucky. Earth ended up in the Goldilocks zone with liquid water, a protective magnetic field, a stabilizing moon, tectonic plates recycling nutrients, and a life-friendly atmosphere. Every single one of those things had to go right. And they did. And the wildest part of all this, our solar system is just one out of hundreds of billions in the Milky Way alone. Whatever questions you have about space, keep asking them. That curiosity is literally how we figured all of this out. If you made it all the way here, thank you. If any of this blew your mind, hit subscribe and drop a comment with your favorite fact from this video. I'll see you in the next one.